be presenting his talk, Low Power Networks, Challenges and Opportunities. So I will you.
Thanks very much. It does not.
Okay.
Yeah. Sorry. So thank you very much for being here. I'm Nicola, and today I will introduce low power networks and what I believe are the challenges and what are the opportunities on this kind of networks. So first of all, we need to define what are low power networks. I hope that you are familiar with a bit with communication networks. So this is really a very traditional view of the internet and of the architecture that we can envisage in this kind of networks. There are client-server communication and peer-to-peer networks. These are the typical architecture that we may find over throughout the internet. With the advent of very low-power devices that can be linked and plugged into the internet wirelessly, we have this low-power network that could be of any kind of, which can be based on any kind of technology. The important thing is that they are proxy to the internet, and any of the user throughout the internet can contact any of these devices into this low-power network. And in fact, each of these devices can act as a server, in fact. So the challenge is to make this network work really properly in a way that, since they are very low power and they have limited communication capabilities, to make them easy to be contacted and also easy for them to be configured to transfer data and for monitoring purposes. So in this context, the IoT, it's more associated with this concept, pervasive computing. What does it mean? It means two things: that there are a bunch of devices and that there is wireless connectivity among them. More in details, since we are speaking about devices that have very limited processing capability, they are a bit dumb. So we have just to share the computing capabilities, the processing capabilities on several devices. And on the opposite, they should communicate each other. It's like the neurons into brain. Let's assume that the brain is shared, the neurons are spread all around the world. In fact, it's putting the sense that we have on our hands, for instance, to sense the world. This is the idea of the IoT, in fact. So we have a lot of devices with chip circuitry. That means, in fact, cheap, that means that they should cost on around $10 or something. And that they have limited memory and limited processing capability. Of course, the fact that they are far enough each other and that they have to communicate puts a problem of scalability of the system. Because if we increase the number of devices, it increases also the number of communication, but not linearly, but with the square of the number of devices. At the same time, we know that since we are speaking about IoT and devices, billions of devices potentially, we don't want to put a cable to connect each of them to communicate. We don't want also to put a cable to be then powered by current, so that they should be standalone devices. This means that there is wireless connectivity. We need wireless connectivity. That in turn implies that we have a battery-operated device and that they use also energy harvesting. Of course, this puts a problem of limited energy. So we should care about energy efficiency. So the main challenge in IoT networks is to find this compromise between scalability and energy efficiency. In fact, if we design communication protocols that are just scalable, we will easily end up designing something which is energy inefficient. Why? Because to be scalable, devices should be listening for incoming information. They should be reactive. So But since listening for information, it's a power expansive activity, that means in turns that the networks, if it's really reactive, so there is a change into the network, one node gets broken, for instance, we have to react and recreate multipath, not a multipath, well, a routing strategy to let the data flow towards collection point. In this case, we see that there is energy inefficiency on this kind of networks. If we design the network and the protocol, the communication protocols, with just energy efficiency in mind, we will have a restrained scalability, because the most common way to try to reduce the energy consumption is to duty cycle the communication activity, so that they will transmit, for instance, for 1 second, and they will, example. But this means that they won't be listening for incoming information. They won't be transmitting at the right moment when there is someone on the other side listening for those information. So designing communication protocols for IoT means that we have to take into account scalability. I'm speaking about low power networks and not low power wide area networks or short range communication, because I'm speaking about all those kind of networks and technologies that use to connect objects which are fed by batteries. So where we have to take care of energy efficiency. In general, we can distinguish between short range communication and long range communication, even though the short-range ones can be extended to wide-scope communication through multi-hop communication. That means that you have to implement routing protocols over mesh networks, which is pretty complicated, in fact, and increases, in turn, the cost of the devices, because they should be a little bit more capable of having also some firmware on top of that. So what are the distinctions between these kind of networks? Let's see here this diagram. For instance, in the most common scenarios, the basic one, we have just a proxy, a device which is just linked to a laptop, which is just a proxy to the internet. And this device acts as the proxy between the network, the low power network, and the internet. In the most common scenario, we have just short range communication between, in the order of 50 meters of distance, where there is a device that communicates. You see the green arrow here with this device. Of course, here we have a limited scope, around 50 meters around me. It's like communication technique like wireless personal area networks, wireless body area networks, these kind of things. We can include also the a very easy forms of a Zigbee network or a Bluetooth. Of course, if we extend the scope of the network of short-range communication, we have that, for instance, we have to implement multi-hop routing. And here we have this column with an increased delay, of course, because you have to receive and forward the packet until it reaches the final sync of the application. Of course, this implies also low energy. The short-range communications implies also low energy consumption, because transmitting over a short range means that the power consumed is proportional to the distance. So if we increase the size of the transmission, the power consumption increases as the square of the distance. So we have to take into account that if we move to a long-range communication, we will consume a lot of energy for a single transmission. So we have to take into account that the communication should be very efficient. So we should be sure that there are not many collisions. Or if we don't care about collisions, we have to make sure that the generation rate of the application is very low. So with long-range communication, we should make sure that we don't have application that needs a lot of transmission packets to be transmitted over the network. So this is just to show the environment. I've been investigating a lot for short-range communication, but recently, well, in the order of 7 years, I've been investigating low-power wide area networks, which are a class of low-power networks that, as you can see from the name, it's wide area networks. We are speaking about long-range communication, and the main architecture that we can see in all the technologies fitting this kind of technology, we have here low-power devices that communicate over long distances with gateways. And in many cases, a single end device can communicate with all the gateways in its transmission range. And all these gateways will forward the replicas of the frame that they have received to the server. Here we assume that there is a reliable network. It could be anything. It could be also the gateways can be connected through the fiber, for instance, but it could be also satellite network as well. But we assume we don't care about the communication on this link. We assume that it's reliable. The bottleneck is this kind of network here. And on this kind of network, we have low energy, low throughput, low processing, and low memory capabilities. Among all the technologies, I've focused a lot on you may have heard about LoRaWAN, long-range wide area network. But actually, I decided to work on LoRaWAN, which is LoRa, the LoRa technologies, because my sister's name is Laura. This is the main reason why I've shifted to this network. I'm not kidding. Her name is LoRa. And I have also a project with her, well, but I will speak about that later. So what we have done on this kind of network, it's since it's a new technology, which is based on this protocol, which is called Pure Aloha. I don't know if you are familiar with that. But in a few words, it's the goal of this protocol is if I have something to transmit, I do it. That's it. If there is collision, I will demand retransmission to other protocols. This is the only thing to take into account. But Aloha was thought to be on a single gateway, so with a single base station organizing several communication happening in parallel. Here we have with LoRaWAN the availability of several gateways that can listen to several communication. And imagine that if I'm an end device and I'm transmitting to two different gateways far away from me, it's possible that I'm able to communicate with a gateway or I have experimental collision on a gateway. On the other one, I have the possibility to transmit the data. So there is no collision. So you may imagine that the throughput is higher. So the classical models for this kind of for pure Aloha networks should be extended to multi-gateway situations. Of course, this has already been done into the literature, but we have also to take into account that into this kind of network, we have to make sure to design the network and to relate the throughput to the density, the average number of devices that can be into the network. If we fix the analysis on a specific number of devices, we are making a really a design of the network which is specific to the specific number of devices that are into the network. It's better to be a bit more general. So the idea that I have started with is to design a network with, you can see here, these black dots, which are the positioning of the gateways, and you can spread with the Poisson law everywhere on this network, the device. In fact, this scenario was designed with a goal in mind, to allow that each point on this topology is reachable by at least 3 gateways, to allow also low power radio localization, for instance, and to have a backup system with respect to GPS, for instance. Based on this analysis and on this design, I end up finding, well, this is just to show that there is some maths behind that, but nothing special. I won't go into the details of the derivation of these formulas, but just to say that with if you are a pervert on mathematics, you can arrive to this kind of formulas. That's it. So here I've pictured what is the throughput of an Aloha networks where there are plenty of gateways, multi-gateways deployments. When we assume that at least we want to make sure that the frame is received to at least one gateway. So just one. But if we want to have radio localization, for instance, we have to restrict the analysis and let the frame that should be received by at least 3 gateways, and we have this other formula. So we have found that there are plenty of throughput formulas further than the single gateway one, with that allows also the reception of packets with just one gateway. In fact, those models are probability models. So they are just functions, mathematical functions, but we have to stick a bit more close to reality. Well, simulation is not reality. We all agree on that. But at least it's an approximation. And it's an instrument that we have built at class. And the idea is to validate the simulation with the models with the simulation. But as well, if we are pretty sure of the model, we can validate also the simulation model. Here in these figures, the blue lines here are related to the first formula here, the red lines to this formula. So we restrict the analysis to the blue one. We can make the same reasoning for the red lines. The blue lines here, there are 3 lines. You can see here with these strings here, it's the probability model. The dots, it's results coming from simulations, just averages, statistics. And we see here that probability and statistics converge, and it's fancy. Well, this is my conversion of the. So, and we can see that the dots are within this here. So using a Poisson generation of frames into the simulation, we have achieved the results that we were expecting. So the model fits the simulation. So we have validated the model. Of course, if we change a bit into the simulation, the simulation parameters, for instance, we want to introduce some duty cycling policy, we obtain this line here, which is a bit far from the model. But at least since we have validated the model, or vice versa, we have validated the simulator, so the 2 things converge, we can trust the simulator. And maybe the simulator, if we are not able to find mathematical models or something, we use the simulator. And that's it. Since I'm more pervert about mathematics, I pushed a bit further the analysis of the multi-gateway formulas. I was assuming that there was not anymore a specific placement of the gateways, so with honeycomb, but any position of gateways. And I found this super fancy formula here that I'm going to explain in the next 10 hours. I'm just kidding. So the idea you can see here, this is what I was explaining before, that an end device can transmit to several gateways, to 2 gateways, but here there is a collision. Here the collision, there is no collision, so the packet is the same. And the idea is to find with modeling any multi-gateway deployment, duty cycle limitation, buffer of any size, so taking into account social security theory, etc. And also taking an effect, which is the capture effect, that it's really something that we discovered with real experiments, in fact, because simulation is something that stays, it's virtual, but with real experiment, we find that there are problems that we cannot imagine before. Just to show something that I forgot to say, you can see here the maximum, it's around 1 error, more than 1 error. That means we are using 3 channels, so the throughput of this network is higher. So this is proof that with many channels, but also with many gateways, the throughput of classic pure Aloha networks, where in the classic pure Aloha networks, the maximum was around here, it's really increased because we have several gateways and several channels. Another thing that we have been doing, since we were not okay with pure Aloha, we were trying to also to have more throughput. We have decided to try to find some protocol design on the top of LoRaWAN. You may know that LoRaWAN works with class A, so it's pure Aloha. What is the idea? If an end device has to transmit, it does it, and then it waits for 1 second that it opens a reception window. If there is something that it's going to be received, it will be transmitted. If there is nothing there, there is also another reception window where a frame can be received. But of course, this communication, it's bidirectional, but it's not symmetric. Because if a server or someone from the gateway wants to communicate, to push some information to the end device, it has to wait to be contacted first, to send something and piggyback into the acknowledgement. To go beyond this scheme, still in LoRaWAN, there is the possibility to have another communication scheme that allows the end device, to be synchronized to the network and to regularly open a reception window to receive some information from the server, which are asynchronous with the acknowledgement following an uplink transmission. In this case, of course, we have an energy consumption which is higher. Because to listen for beacons, we have to still listening. So we have to keep our radio on and waste energy. And in fact, this access, it's also, even though it's thought to be for receiving information, for uplink transmission, we have still pure Aloha communication, which is not good. In fact, we wanted to at least double the communication scheme and the throughput of this network by implementing slotted Aloha on the top of LoRaWAN. To do that, it's very easy. We have just changed small things into the specification. I mean, we have read the specification and found what are the small details that we have to change to have also slotted access. And we end up also having this kind of access. We have baptized this access class S. S stands for slotted. Yeah, there are three classes, default classes in LoRaWAN, A, B, C. We have put S, so we are sure that no one else was deciding for this. So S, it's our. We have reserved our name for the class. In that case, we can see here that we can also schedule information because we have slotted the time and each slot, it's long enough to have the transmission or the reception of the maximum size packet. Based on that, we have compared what would happen, into simulator if we use pure Aloha or slotted Aloha, and in fact, we have seen that with this minimal modification to LoRaWAN, we can implement slotted and we can double the throughput. See, further than that, we have to analyze also what is energy efficiency. And we go back to the balance between scalability and energy efficiency. Here, we can see that here, because this is the energy efficiency defined as the energy consumed for successful transmission based on the overall transmissions, the overall energy spent for communication duties. It includes also the overhead due to the signaling protocol. We can see here, this is the energy efficiency of class A, so the basic LoRaWAN access. And we have compared that with the class S. Here it's if we use class S without skipping beacons, but if we start not listening to beacons, so instead of listening to all beacons that arrive, we listen 1 out of 10, for instance, we save energy. So we can see that the energy efficiency grows up until here, where we have 1 out of 10 beacons that has been listened. Of course, this puts a problem of the synchronization of the system, and we have to take into account of this situation. We have done some papers also on synchronization and also on the problem of the drift of the time of the clock of these devices, and we have done that with the real hardware as well, because this is something that cannot be simulated. As we can see here, these two lines cross here. So we can see that before here, class A is more energy efficient. Here it's better to pass to class S. Based on this evidence, we have designed a protocol to automatically decide that an end device should pass from class A to class S and vice versa. So we have to sense the network, and we have designed this algorithm. this architecture. We have network probing. We see what is the throughput, what is the situation. Based on that, we understand what is the generated traffic. Based on the generated traffic, we can understand, if we know that all the devices are in class A, if we see that the throughput is increasing because there are plenty of devices, or the devices are transmitting more frequently, for instance, there is an alarm and they are sending more data of temperature, automatically the network will understand that we have to shift to class S. And this is what we are doing here. And this is an online operation that we can see here. For instance, this is an event that is happening here in this moment. And after some time, all the devices starts to shift on the class S. As you can see here, the red line here, it's what would happen if we didn't have class S. The blue line, if we have class S. This is the throughput. The throughput is increased in the case when we use this mechanism. And also the energy efficiency. If at the beginning the energy efficiency is better when we have no implementation of class S, in the end, when we have plenty of devices that are joining the network, so we have an increased throughput, shifting to class S, it's better because it's also more energy efficiency. This is to show also the trade-off that we are doing. These are the challenges that we have afforded. Let's speak about the opportunities. I will go very fast. There are just other 4 slides. Actually, the 4th one is just to say questions, but without responding to the answer. So it's just 3 slides. First of all, one of the applications is to use this protocol design and performance evaluation to grant to satellite communication, as you can see here. And these are the main 2 architectures that can be used, even though this is something which is still on LP1 on the ground. But the most challenging is this one. And I've been also writing a paper with Sandra and also with Juan, for those that know. Another possibility is to use radio localization. This is the opposite problem. We don't want to use satellites. An important thing with the radio localization, right now, if you have your phone, you have GPS, so you are receiving packets from the satellites that do not collide, actually. With this system, it's the opposite. We have the device send something to the gateway, so there are collisions. It's the opposite way. If the packets are received to 3 gateways, we can triangulate the RSSI or the time difference of arrival. What has been discovered recently is that it's better to use the time difference of arrival rather than multipath fading that can affect, and also all the problems at the physical layer that can impact the transmission and the reception of the packets. The main problem with time difference of arrival is that the gateway should be synchronized on the same concept of time. And magically, in all papers working with the DDoA, they still use GNSS to synchronize the gateways. The idea is that we don't want at all to use also the timing from GNSS. It's just to create a backup solution. Imagine that they switch off GNSS for some reason. We should be able at least to have a low, how can I say, with a resolution which is not the best, we can content ourselves with some radio localization. Let's assume that we want to localize a pet, or we want to localize also dementia patients, for instance, that they have forgot to have their phone with them, and we want to localize that. You can see also the application also in social life of this application of LoRaWAN. The idea is that we have a signal which is, a device which is put on the middle of a triangle between the 3 gateways and transmit on the circumcenter. So when it sends the packet, it synchronizes the gateways because the packet arrives at the same time on the transceiver of the gateways. And after that, we receive another packet from somewhere else. So we don't know the position of that gateway. Based on this time of arrival, on the time difference of arrival with respect to the previous signal, we can reverse engineer the distance and so triangulate the signal. We have done simulations, so I'm not speaking about that this is going to be something that it's going to happen really, because the idea is to work on real hardware for that. This is the only thing that matters. We have found that if the gateways are 8 kilometers apart on an equilateral triangle, we have that the maximum error into the triangle is 23 meters, which is pretty acceptable with respect to the 100 meters in a very good condition that we can achieve with LoRaWAN, with the TDOA, but with GNSS. The problem of GNSS, of that architecture, is that the signal of timing signal should be passed from one interface, the GNSS signal, to the transceiver of LoRaWAN. In doing that, we add random delays that affect also the precision of the estimate. And last topic, using also LoRaWAN for healthcare services. This is the frontier. And on that, I want to take back to speak about my sister, and we'll finish. I will say the last things. My sister, she's a physician, in fact. And the idea was to work with her on a paper on LoRa, where it appears also her name as an author. And there is also another friend of mine whose surname is LoRa, exactly that. And write a paper, healthcare system in the name of LoRa. Oh, that's it, I want to contribute. So these are the things that can be done with LoRaWAN. And that's it. Thanks for your attention. And
So thank you, Nicola. You can take a water from there if you want, because we all were but a bit late.
what?
Yes, you can take water.